Okay, here's example number 4 from our notes. We have a mountain climber, and this mountain climber encounters a crevasse in an ice field or in a glacier, and so he has to jump over this. So think of it like this. Here's the edge of this crevasse, and he's standing up here and needs to get down to here safely without falling down into the pit. Okay, so what are we told about this? Oh, we're told that the opposite side is some distance lower. Okay, so this distance right here, how much lower is that in the y direction? That's 2.75 meters. 2.75 meters right there, okay. So you might say that is delta y, right? That'll come in handy later. And what else? We're told that the gap itself is 4.10 meters. Okay, that you might say that's not really delta x. No, I probably shouldn't call it that because that's simply what the mountain climber has to clear. And the one question refers back to this. But that at least gives you a sense of what we're looking at here. Okay, and so our mountain climber gets a running start. A running start in the horizontal direction, and so that is x. I'm sorry, not x, but vx, right? That's the velocity x initial right there. That's the initial velocity in the x direction. You know, I'm going to make my pen a little bit smaller. Sorry about that. A little bit finer there. Okay. What else do we know? Well, let's just start writing things down. So our x position. So right here. That position right there, what are we going to call that? Well, let's call that 0. Okay, so starting from 0. So x initial equals 0 meters. Our x final, that is, if he jumps exactly over the opening, gets right to the other side. Because what we're solving for actually is, in fact, I'll write this at the top here. Part A is asking us minimum velocity in the x direction, or initial velocity in the x direction, to clear the crevasse. Okay, well, in order to clear it, you need to get exactly the crevasse's width over it. So in this case, in order to solve for the minimum velocity, we're going to make our x final, that is our final position, be exactly what we need to clear it, and that's 4.10 meters. Okay, and the question is, what's the initial velocity in the x direction that's required to do that? Okay, well, we have some y values as well. Let's write them down here. Our y initial position, what is that? Well, if that x is 0, that y is 0, we'll call that 2. So let's just call that 0. Okay, our y final, what's our y final position if he makes it to the other side of the crevasse here? Well, that's 2.75 meters down, right? It's changed by 2.75 meters, so it's negative 2.75 meters because it's changed in the negative y direction. What's our starting velocity, our initial velocity in the y direction? Well, he has none. We're going to say he has a starting velocity in the x direction, but none in the y direction. VYI, that's 0 meters per second. He's not starting moving up or down. He's starting moving sideways. So the initial velocity in the y direction is 0. Oh, you know what I forgot up here? Is there any velocity in the x, oh sorry, is there any acceleration in the x direction? That's no. 0 meters per second squared. But there is a velocity in the y direction. And that's what? We all know that to be negative 9.81 meters per second squared. And my dog is scratched at the door here. Hey, sweetie, how you doing? That's Hannah. She was feeling sick today, so she's looking for company. Okay, so we have all our x written down as well. And there really shouldn't be anything else we need. Now, the question is, how do we find the minimum velocity required to get over this crevasse, but also fall right to this lip right here? Well, two things are happening. The mountain climber is moving that much in the y direction and moving that much in the x direction. That's all that's happening. Do either of them have anything to do with each other? Well, no. We said that with projectile motion, that y and x motion are absolutely independent of each other. But one thing they do have in common, and here's a hint to solve this. Hint. Solve for time. Solve for time in y direction. Why? Well, because we do have an acceleration in the y direction, we have an initial velocity in the y direction, and we have a displacement in the y direction, and we can do that. And the amount of time that it takes to move this much in the y direction is exactly the same amount of time it takes to move that much in the x direction. So let's solve for time regarding the y direction, or actually both directions, really. So for time, y final equals y initial plus initial velocity in the y direction times time plus 1/2 times acceleration times time, acceleration in the y direction, sorry, times time squared. Now you're probably saying, well, where did I come up with that? I just looked at my y's and saw what I have. I have an acceleration, I've got a displacement in the y direction, I've got initial velocity in the y direction. So we should be able to use all this to solve for t, to solve for time. And in fact, some of this goes away anyway. Since our initial velocity in the y direction is 0, that whole section becomes 0. So we should now be able to solve for t. And we need to do some rearranging here. Let's see. Y final minus y initial equals 1/2 times acceleration times time squared. So I'm going to bring my my 2 up from the denominator. I'm going to multiply both sides by 2 and divide both sides by a, right? Oops, I don't want v, I want y. Y final minus y initial times 2. Hannah, stop that. My 12-pound Boston Terrier is licking my feet, and it's very distracting. And we're going to divide that all by acceleration in the y direction. That equals t squared. Well, one more thing to solve simply for t is to take the square root of both sides. So t equals the square root of 2 times yf minus yi over acceleration in the y direction. Well, what does that come out to be? That's a square. I can't keep my square root sign square. That's a little better. So that's 2 times, what's the y final? Negative 2.75 minus y initial, that's 0, over the acceleration, negative 9.81. I'll just keep the units out. Negative 9.81. We know that our answer is going to be in seconds. So if we calculate all that, our time in seconds comes out to be 0.75 seconds. That is, we use what we knew about the y to solve for time in the y direction, but it just so happens to apply, the time applies to the x direction as well. So the amount of time it takes for the mountain climber to fall down 2.75 meters in the y direction is the amount of time that he has to move over the crevasse. That's 0.75 seconds. So for minimum velocity in the x direction, and this is just a continuation of part A, for minimum initial velocity in the x, how do we solve for that? Well, we have a time, t equals 0.75 seconds. We have a distance, the minimum distance that needs to be covered is the distance in the x direction, right? Delta x is 4.10 meters. So we should very easily be able to solve for initial velocity in the x direction. Now you might say, well, what about final velocity in the x direction? Well, remember, they're both the same. Velocity in the x direction, initial, final, it's all the same because there's no acceleration in the x direction. So what is that? Well, that's displacement in the x direction over time. So that's 4.10 meters per second, or meters, sorry, over 0.75 seconds. And that gives us an absolute minimum x velocity of 5.47 meters per second. So a mountain climber has to be moving horizontally at 5.47 meters per second to just barely get across that chasm, to get across that crevasse and make it just to the lip of the other side. He's also falling too, but we use the falling information, vertical information, to find the amount of time he has to make it across, and that helps us solve for our necessary velocity in the x direction. Okay, so that was part A.